So we're going to begin our next unit on rational expressions, equations, and functions. We are going to start by talking about domain restrictions and simplifying rational expressions. We're going to practice multiplying and dividing rational expressions. We're going to practice simplifying complex fractions. We're going to add and subtract rational expressions, and we're going to solve rational expressions. And then after we complete all of that work, we will begin to graph rational functions and see what they look like. Today we're going to have a little sneak peek as to what graphs of rationals look like, but first we're going to talk about what a rational expression is. And we just finished our polynomials unit, if you can think back to early March. But a rational expression is an expression that can be written as a quotient of polynomials. So if we have a polynomial, p of x, over another polynomial, q of x. If p of x and q of x are polynomials, that quotient or that fraction is a rational expression. And a rational function is a rational expression that is a function. So if we now have f of x equals a rational expression, and we graphed f of x, we need to make sure that it passes the vertical line test in order to be a function. So we're going to graph rational functions later on this unit, but we're going to really focus on rational expressions to start off. So a rational function is undefined when the denominator is 0. And then we must look for the domain restriction. So the domain restriction is going to tell us a lot about what the graph will look like. So for these three examples, I want you to find the domain restriction of each rational function and then to write the domain using interval notation. This is a little bit of a throwback here, so we have to make sure that we remind ourselves what interval notation is. But if this denominator cannot equal 0, we need to find out the value for when it does equal 0, so we know that x cannot equal 6. So in interval notation, we can say negative infinity to 6, and then 6 to infinity, because we're not including 6 at all. So that would be our domain. And this is our domain restriction. So to find the domain restriction for the next two, we need to set the denominator equal to 0. So if I set this denominator equal to 0, we can factor it. So x equals 5 and x equals negative 2. So our domain restriction is x cannot equal 5 and x cannot equal negative 2. If we plugged in those values into this function, that would give us a 0 in the denominator, making it undefined. So negative 2 would come first in my interval notation. Negative infinity to 2 union, or negative 2 rather, negative 2 to 5 union 5 to infinity. So getting us to remind ourselves how to write our domain in interval notation. And now for this next one, notice how there's no variable in the denominator. So there is no domain restriction. Okay, so if there's no domain restriction, the domain is negative infinity to infinity. So I want us to have a look at each of these functions graphically. So I went ahead and graphed each of them in Desmos. So for this particular graph, we said that x cannot equal positive 6. So I know I'm kind of zoomed out here, but if we envision this line being x equals positive 6, notice how the graph doesn't cross this line. So as this gets closer and closer and closer, it will get closer and closer to this line, but it won't touch. In the same way that this part of the graph will get closer and closer and closer to x equals 6, but it won't touch the graph. So that vertical line that we're drawing there is called an asymptote. And that's going to be important when we start graphing, but right now we're just kind of getting used to what rationals look like graphically, and then we can work with them a bit more later on in the unit. So for this one, we said that x cannot equal -2 and x cannot equal 5. So here's -2. If I draw this dashed line, this vertical line, and then 5 is right here. So there are 3 parts to this graph. And notice how when this graph gets closer and closer and closer to this dashed line, it's not going to cross it. In the same way here, it can get closer and closer and closer and not cross. So seeing how those lines work, these vertical asymptotes, they're vertical lines and they're asymptotes, the graph will not cross this. Again, just trying to get you familiar with this language so that when we do graphing, it won't be the first time you've heard that word. Okay, so this one, our domain was -infinity to infinity. And notice how it's an x squared in that numerator, so it's a quadratic. But h of x can also be rewritten as x squared over 4 minus 9/4, or 1/4 x squared minus 9/4. So we have this stretch factor, and we have a parabola. So that's what this graph will look like. It's still a rational function, but the specific type of rational function is a quadratic, and it creates this parabola. So now we're going to talk about simplifying rational expressions. And to simplify each expression, I want to show us what to do and what not to do. So I'm going to start off with what not to do. We have to think about finding factors to reduce. What not to do would be this. No way. You are not allowed to do that, because here we have a subtraction between the two. So what we have to do first is factor each expression. So this numerator is already as 3y cubed, but if we factor the denominator, we have a GCF of 3y cubed, and then we're left with 2y minus 1. So when we reduce, we are reducing factors, not terms. So this, on the right side, what not to do, you'd be reducing terms, not factors. So there has to be multiplication in between. So when we reduce, we're left with a 1 over 1. So that reduces to 1 over 2y minus 1. So that is fully reduced. So make sure we're keeping in mind what to do and then what not to do. All right, so now for this one, notice how this top one can be rewritten as x plus 2 times x plus 2, and the denominator, x plus 2, x minus 2. So we have some factors here that we can reduce, and so we are left with x plus 2 over x minus 2. I like keeping the parentheses around these binomials, so I know I cannot reduce the x's, I know I cannot reduce the 2's, and make that mistake of what not to do. So keeping the parentheses around those will be helpful. All right, let's look at this next one. So factoring the numerator and then factoring the denominator. So in the numerator, we have 5x and x, and then 1 and 1. So we can go through that a little bit simply. The signs are the same in the factors, and the signs are both minus, so that was pretty okay to factor. How about this denominator? So we have 7 and 1. So if I put a 7 here, I would have to do 3 times 7, that's 21. That's very far away from 4. So I'm going to put my 7 here and my 1 there, and then figure out which sign is going to be, which factor is going to be positive and which is going to be negative. So we have a positive 4. So I want this to be a negative 3x and then plus 7. And now look, we can reduce these x minus 1's here and be left with 5x minus 1 over 3x plus 7. Okay, so this next one. We have x plus 5 over 5 plus x. Remember, addition is commutative. So anything divided by itself is 1. Subtraction is not commutative. So when we're looking at this, notice that we have x minus 6. If we wanted to get another x minus 6 in the denominator, what if we factored out a negative 1? And then we switch those around. Now we have common factor, and we have this negative 1 that it reduces to. So these are opposites. So anytime you have opposites, so x minus 4 over 4 minus x, those are opposites that reduces to negative 1. So we have to be careful when it comes to expressions like this, and then also when it is addition. Okay, so why don't you pause and try this one and see how this one works out, and then we can come back to it. So I'm going to go through it. If we take out a 3, we're left with 1 minus x squared. And then the 1 minus x squared can keep going to 1 minus x, 1 plus x, because it's a difference of 2 squares. And then the denominator can be rewritten as x plus 2, x minus 1. Okay, are you with me? So now that we factored everything, the only common thing we have are these. But notice how we have 1 minus x and x minus 1. So when I reduce that, I'm going to put a negative 1 up there. So we have 3 times negative 1, which is negative 3. And then we have 1 plus x, or you can write x plus 1. Either would work. And we can leave it like this. You do not have to remultiply everything out in your final answer. You can leave it in factored form. So just keep that in mind. Once you factor, keep everything as factors. Okay, so let's look at this numerator. What do you notice about this? Sum of 2 cubes. So we have to remember our factoring. So the signs are the same. Opposite, always positive. X squared, 3x, 9. And then we have another x plus 3 down there, which reduces. We're going to need to remember our sum and difference of 2 cubes factoring. That's going to be important. Okay, for this next one, notice how in our numerator we can factor out a 3, and we're left with x squared plus 2. And in our denominator, we have 4 terms. So how would we want to factor those 4 terms? Grouping. So I'm going to do the grouping over here so it stays away from that other work. But if I take out an x squared, I'm left with x minus 3. And then I could take out a 2 and be left with x minus 3. So we have x squared plus 2, x minus 3. So x squared plus 2, x minus 3, and now we have this common factor. We're going to reduce. So we're left with 3 over x minus 3. Again, if we place parentheses around this, it will avoid us reducing these 3's. So that's the end of this lesson, and please go back if you need anything reviewed.